Okay, so our second speaker is Ted Slaman from Berkeley, and he's going to talk about aspects of Hausdorff dimension. So thank you, Ted.
Okay, thanks. Thanks everyone for coming to the talk, and thanks for the organizers for setting up the meeting and including me. So it's the topic I want to discuss a bit today is a joint project I've been working on with Jan Reimann for the past year or so, a little bit more. And it's looking at aspects of Hausdorff dimension, and especially with regard to gauge functions. So what I want to talk about is how logic, especially recursion theory and effective, well, even general set theory, suggests lines of investigation into geometric measure theory. And so I would say sort of the basic properties of Hausdorff dimension. And the particular thing that I want to talk about is a problem that's emerged as a sort of central with regard to strong gauge dimension. Okay. And in particular, strong gauge dimension 0. Okay, so here we go. A gauge function is a function from the positive real numbers to the positive real numbers, which has the following properties. It's a continuous function, it's increasing, and the limit as t goes to 0 from the right of h is equal to 0. Okay, so if you think of things happening as you come in from right to left, as the argument decreases, it's a function that is continuously and monotonically going to 0. And the classical examples of such functions are the power functions. You take a power s something greater than 0, and let h of t be t raised to the power s. Then, if you have a gauge function, you can define from it a measure. And this is a small generalization of the classical Hausdorff measures. So here's the definition. It's worth, if you haven't immersed yourself in Hausdorff dimension, it's worth lingering for a moment over the definition. So capital H stands for Hausdorff, little h stands for one of these gauge functions, and the outer measure of a set E is the limit as delta goes to 0. And this is as delta gets smaller and smaller, we're looking at the structure of the set E in finer and finer granularity. Okay. So the limit as delta goes to 0. So you look at the limit as the granularity of your assessment of the set becomes finer and finer. And then this part is the usual definition of an outer measure. It's the infimum of over the set of open or closed covers of H is giving you telling you the size, and the size of a basic open set is given by its diameter. Okay, so you look at the close, depending on whether you include the endpoints in the intervals that you're discussing, you look at the open covers, say, and you demand that the granularity of the cover, the open intervals that show up, have to be of small diameter, and then you take the sum of the measures of the open sets that are constituting the cover. Okay, so F is a collection of open sets covering E, and the D of F of I is the diameter of F of I. Okay, so this is the usual. If it were a Lebesgue measure, you just look at the inf of the open covers, and each interval would have size its diameter. But as you vary H, you can change what you think of as the measure of a basic open set. Okay. When you look at the example that we just discussed previously, when h of t is t to the s, then this quantity we just defined, the h outer measure, is the usual s-dimensional Hausdorff outer measure of the set E. So this is a generalization of what may be more familiar. The advantage to using gauge functions is that they provide a more finely graded calibration of measure and thereby of dimension than is given by the family t goes to t to the s. There's a lot of functions that can assign larger measure to intervals than t to the s does, but are still giving smaller, asymptotic measure than t to s plus epsilon for all epsilon. Okay, now gauge functions are naturally ordered. So we're gonna, this one which one is less than the other? We're gonna write h is less than g to indicate that the limit as t goes to infinity of g of t over h of t is equal to 0. So this is not to say that the value that g is pointwise above h, right? It's the opposite of that. Instead, it's taking the order in accordance with the associated dimension. Okay, so for example, let's look at this example. If you take t to, this is a natural exponent, we'll see in a minute, t to this exponent log 2 over log 3, that thing is less than t to the 1 because log 2 over log 3 is less than 1, and so the limit of that ratio is equal to 0. But a set that has dimension 1 is in the usual Hausdorff dimension, is a set where you'd be looking at the linear h measure versus this Cantor middle third set measure. So that g is bigger than h means dimension g is greater than dimension h. Okay, it's easier if g is greater than h. It's easier for a set to be g null than it is for it to be h null. Okay, the Hausdorff dimension of a set this is the classical dimension. The Hausdorff dimension of a set is, oh wait, I have to uncover something here. Okay, the Hausdorff dimension of a set in the reals or in 2 to the omega, etc. It's the number d such that whenever d0 is less than d is less than d1, so if d is sandwiched between d0 and d1, then the d0 outer measure of a is infinite, and the d1 outer measure of a is equal to 0. Okay, so the Hausdorff dimension is the number where these measures transition from infinity to 0. The example from the previous slide is the Cantor middle third set. It has dimension log 2 over log 3, and it's null with respect to linear measure, and it has infinite measure for anything that's less than this, for any exponent less than this quotient. So it's a sort of canonical example of a set that has fractional Hausdorff dimension. Now this clarity of the way that Hausdorff dimension works, and I should say that inside here at D, right, HD of A can realize all the usual possibilities. Okay, so knowing the Hausdorff dimension of a set does not determine the Hausdorff measure of the set at its own dimension. Okay, everything is possible, and that sort of complete account of how these measures work transfers partially when you think of finer notions of dimension given by gauge measures. So here are the similarities. First of all, if HA is finite and H is less than G, so G says that it's easier for sets to be null. If the outer measure for H is finite, then the G measure is equal to 0. So if you have that the outer measure is finite, then it becomes identically 0 afterwards. And similarly, if the outer measure is not 0, then for the j's to the left, hj of a is infinite. So there is this situation where you can go from infinite to finite to 0, just like in the case of classical Hausdorff dimension. But there are some differences. Namely, if HA is equal to 0, then there is a J such that J is less than H, and HJ of A is equal to 0. So it's knowing that so if you have something like exact gauge dimension H, you can't have H outer measure equal to 0. So that's a theorem of Besekovich. The study of gauge functions and so on really concentrated in the 1950s. And it was Besekovich and I think what you might say the school of Besekovich that really figured out a lot of the standard facts. Okay, so what arises in this study is an interesting phenomena. So we'll say that a set is sigma finite for the H Hausdorff measure if and only if A is a countable union of sets AI, such that each one of these AIs has finite measure. Okay, so an example of a sigma finite, an example of a case that's sigma finite is if you look at the real line for linear measure. You can divide it up into, it has infinite, linear measure is Lebesgue measure. It has infinite, the whole line has infinite measure, but you can break it up into a countable collection of finite intervals, you know, the interval from 0 to 1 and 1 to 2 and so forth. And each one of those intervals has finite measure. So that's an example of a set that's sigma finite. So sigma finite is like looking at a sigma algebra. Sigma stands for countable. Okay, so there's an improvement from the previous slide. If A has non-zero H measure and J is less than H, then A is not sigma finite for J measure. Okay, so as soon as, if you have a situation where, like a line segment, so a line segment has a non-zero linear measure, it's not sigma finite for any, it has non-sigma finite measure for anything that is less than linear. Okay, now, and I can see I'm really hustling through this material. I'm happy to pause for questions. I can have my chat window open if somebody wants to ask something. Okay, so now, the classical theorem. If you have an analytic set and it's not sigma finite for the gauge function H, then there's a compact subset of that analytic set that is similarly not sigma finite for H. So this is what's called a capacitability theorem. The non-sigma finiteness of an analytic set is supported by a compact subset of that analytic set. So it's like the fact that Lebesgue measure, if you have a set that is has positive Lebesgue measure, then it has a closed subset that has positive Lebesgue measure. You can approximate the measure of a set by arbitrarily well by looking at its closed subsets. So here, this similarly happens for analytic sets and non-sigma finiteness. If you have an analytic set, so a sigma 1,1 set, for example, and it's not sigma finite, then the size of that set is supported by a compact subset. So it's for me, anytime I see a theorem that applies to analytic sets, my first reaction is to ask, is the hypothesis of analytic necessary, and is it sharp? So this is a theorem from the 50s. So that this is before the sort of explosion of results in set theory took over, and we'll see something in a minute. Okay, so a set has strong dimension H, if and only F. For all F, if F is smaller than H, then HF of E is equal to infinity. And for all G, if H is smaller than G, then HG of E is equal to 0. Okay, so strong dimension H is a generalization of having Hausdorff dimension S. It would not talk about arbitrary gauge functions, but talk about only the gauge functions that come from exponentiation. And then a limiting case is E is strong dimension 0 if and only if for all G, HG of E is equal to 0. So there is no gauge function that corresponds to 0. So it's a limiting case. So a good example, a line segment within the plane has strong dimension 1. And that goes with regard to what I was saying before. Okay, so now I think looking at gauge functions is interesting. So I'm used to, because of experience, used to thinking primarily inside the line and just sets of reals. And even within there, I usually don't think about reals. I think about elements of 2 to the omega or omega to the omega. But this notion of dimension is more generally, it's better to think about it in other contexts. Namely, it makes more sense, and you can sort of see its value in other contexts. Like if you think about a curve sitting inside the plane, like a parabola, for example, that thing has dimension 1, and it's sort of better. I don't know. I find it more compelling to think about examples like that than to think about weird subsets of the line. And it's a natural thing that a curve in the plane has dimension 1, but in any intuitive sense. And these notions of dimension capture that. Okay, so now, Besekovich, 1956, and then generalized by Rogers in 1962. If you have a compact set and it's not sigma finite for a particular gauge function H, then there is a G. This is an overspill property, right? There is a G such that G is greater than H, and E is not sigma finite for G. Okay, so this means that you can't what I wrote down here. If E is compact, and then it can't have strong dimension H and be non-sigma finite for H. Okay, so if a set is if you have a compact set and it looks large really large with regard to the gauge function H, then H does not characterize its dimension among all the possible gauge functions. And that fact, because by the Davies Capacitability Theorem, is true for analytic sets as well as compact sets, because the non-sigma finiteness of an analytic set is supported by its compact subsets. Okay, so there's an interesting fact now that is, and again, it's asserted for compact sets, and then here for analytic sets. So the non-sigma finiteness of a set, if the set is nicely definable, spills over. And of course, it doesn't have a sharp boundary. Okay, so I think there's been a lot in the past few years, a lot of sort of algorithmic information theory and randomness, effective randomness, applied to notions of Hausdorff dimension. So I think it'd be quite an interesting development to find a more recursion theoretic, or in the mode of the kinds of things that Lotz and Mardomo and so on have been doing to give a proof of this theorem, right? So there's a nice problem here. Is there a point to set formulation for sets not having sigma finite measure? So can we algorithmically capture this property? So I don't know how to do that. There was some we can take a look at that again after we see a little bit more. Now, this theorem, like I said, Besekovich proved it for compact, and then it was extended for compact, then it was extended to analytic by the Capacitability Theorem. Besekovich showed a few years after those results that if the continuum hypothesis holds, so that here comes some meta mathematical considerations, some logical considerations. If the CH holds, then there is a subset of the plane such that it has strong linear dimension. So it's not sigma finite for linear dimension. Okay, so it is not sigma finite for the gauge function, which is just the diameter of a set is taken to be its measure, and yet it has strong linear dimension. Take any gauge function which is greater than linear, and the associated measure of E is equal to 0. Okay, so this is an abstract set theoretic construction. If you now the descriptive set theoretic upper bound. If you use, so Besekovich had a construction which was an amalgamation of, he built the set to be an amalgamation of line segments. So it's an uncountable union of line segments with using the CH, the way that they are put together yields strong linear dimension. If you assume D equals L, then you can do that amalgamation in a way that to get that the resulting set is pi 1, 1. So you use the way that this thing was put together was used for other purpose in a paper by Erdos, Kunin, and Molden in 1981. So it's inside L. You can use essentially a version of the maximal thin pi 1, 1 set, but it's not the same. But it uses the same ingredients to adapt Besicovic's construction to get a pi-1,1 example. So the theorems from the 1950s were sharp in that they proved something for analytic sets, the pi-1,1 sets are co-analytic. Their complements are analytic sets. So the theorems from the 50s are in the descriptive sense optimal.
Sorry, Ted, there is a question.
Oh yeah, I didn't see it. Sorry.
Peter, yeah, on the chat.
How do you say? How do you?
Besicovich, yeah.
Yeah, how do you use Besicovich? Yeah, so Besicovic's proof was something like this: you work inside the unit square, and what Besicovich did was, here's the unit square. Okay, here's one. Here's one. And what Besicovich did was chose a very thin. Here he chose some kind of thin. I shouldn't use thin because that has a technical meaning. A special. You choose a special set of y's, and then you just look at all the line segments. That's so you look at this collection of x, y, such that x is in 0, 1, and y is in the special set. So what Besicovich did was he chose a set, an uncountable set, such that any open cover of the rationals is an open cover of that set. Okay, so that's a set that they say is concentrated on the rationals. So that means it's easy to cover the line segments with a line segment has finite linear measure. And so you can, if you take a very small open cover of the special set of y's, and then you use it to extend it, to stretch it out to cover the line segments that are associated with those y's, that's the analysis of this kind of set. Now the thing that you do with Erdős, Kunin, and Malden is they showed that you can get a pi-1,1 set that is special in the same sense if V equals L. Okay. And then putting those two things together gives you that you can implement Besicovich's idea where these things, or this set is pi-1,1. Okay. Thanks for asking the question. Okay, good. Okay, so now there's a connection, an interesting connection with a classical notion due to, I think the notion is due to Borel, and that's my understanding. So this is in Lebesgue measure. So a set E has strong measure 0 if and only if for any sequence of positive real numbers, think of this epsilon E going to 0 fast, there is a sequence of open intervals such that for each I, OI has length epsilon I, and E is contained in the union. The OIs form a cover of E. So set has strong measure 0 if and only if take any sequence of positive numbers, no matter, and think of it as something that's going to 0 extremely quickly. Right? And that's giving you a criteria. You have to be able to cover E by a sequence of intervals that go to 0 just as fast as the given sequence. Okay, so this is a very small set. Right? It's somehow doesn't matter how small the cover has to be. Not only does the cover have small measure, but the granularity of the cover, where you get one interval of this size, and then the next interval is vanishingly small in comparison, and that just continues. And so the strong measure 0 set is it doesn't matter how fast that sequence goes to 0, there's still a cover of the associated behavior. Okay, so Borel conjectured that strong measure zero implies countable. So a countable set definitely has strong measure zero because you can use each point. So the ith point can be covered by the interval OI. In Borel conjecture, that was the best you could do. That was settled by Sierpinski in some years later, who showed that the continuum hypothesis implies that there's an uncountable set of strong measure zero. And that's sort of similar to this concentrating on the rationals kind of situation. And then, but that left open the problem of was this a relative theorem that you needed the continuum hypothesis, or was it just a theorem that Borel's conjecture is false? And that was settled quite a lot later with the advent of forcing by the first sort of subtle application of iterated forcing with countable support due to Richard Laver. And he showed that the Borel conjecture is consistent with the axioms of the set theory. Okay, so this is the Laver's model is quite a special situation. In most situations, the Borel conjecture is false. So in most forcing models, the Borel conjecture is false. Now there's a connection between dimension and measure in this context. Besicovich in 55 showed that a set has strong dimension zero if only if it has strong measure zero. So let me remind you of what that strong dimension zero means, that its outer measure is equal to zero for every gauge function. And then you can generalize that fact. This is another variation on that line segments with the special set of y coordinates. If the Borel conjecture fails, then there is a subset of the unit square, which has strong linear dimension, but is not sigma finite for linear measure. So the natural question, which I'm afraid is still open, is whether the Borel conjecture is equivalent to saying that there is a subset of the plane, or in other contexts, it's equivalent. So that's the question: is the Borel conjecture equivalent to saying that there is a set that has strong dimension but is not sigma finite for the measure associated with its dimension? So that I think in this whole line of investigation, to me, this is the most interesting question. And unfortunately, I don't know the answer. It's a little harder to. The natural thing to do is to look in Laver's model, right? But so far we haven't been able to get a grip on the problem. It has subtleties that don't show up in Laver's proof of the consistency of the Borel conjecture. And the conceptual, and I think, or you could say conceptual or technical problem, depending on your view of these things. The conceptual challenge is to overcome what I see as an intractability in working with the property of an arbitrary set of whether it is non-sigma finite for a particular measure, right? Because being sigma finite says that there is you could take it to be a partition. Is there a partition of the set into pieces, each of which has finite measure? Okay, so the complexity of that partition can be quite high. It's hard to get a grip on that. Okay, so let me what I want to do in the last few minutes here is to look at this problem, the problem of understanding non-sigma finiteness, right? And see its complexity, and maybe get a grip on what non-sigma finiteness means, right? Which will possibly help in trying to understand how the concept works and settle this question that we've raised. So let's look at a particular, let's make everything tangible. Okay, so I want to look at pi01, so effectively closed subsets of 2 to the omega cross 2 to the omega. So something like the context in which these examples that we were looking at occurred, except I'm not going to look in the reals because I don't want to get into representation issues, right, when we start to do the recursion theoretic analysis. So I'm going to look at the unit square, but look at it in Cantor space. And let's also just look at linear measure. So we don't have to get into strange rates of growth for gauge functions. We'll just look at this canonical example. Okay, now, if you look at the problem of having non-zero, or it's related, having infinite measure, right? Then telling whether a pi01 set, right, has non-zero measure is an arithmetic property. You can use the compactness of this situation to give a fairly accessible understanding of it. Okay, so by the compactness of 2 to the omega cross 2 to the omega, by the compactness of the Cantor square, to call it that, we can assume that all the open covers in the definition of what the measure of a set is are finite, because every open cover has a finite subcover. And that means that the definition, just parse the definition, the prima facie definition of saying that the measure is not zero. You can do that by quantifying over the open covers. Those things are all finite. So you can give an arithmetic presentation of what that notion is. Good. And then you have the possibility of using effective methods to analyze, to prove basis theorems and so forth, and get a pretty good understanding of how things work. At least you can get a grip on it from a recursion theoretic point of view. Okay. Now, for non-sigma finiteness, which is, it's like infinitely infinite, let's have a shorthand. Let's let this n sigma f be the set of indices we're going to do the index set calculation. How complicated is non-sigma finite? So let's let n sigma f be the indices for pi01 sets in the Cantor square, such that C is not sigma finite for linear measure. Yeah. And so here's the theorem. Not sigma finite is sigma 1,1 complete. So that, to me, there's two interesting facts here. One is the fact that it's, in fact, to me, the more interesting fact is the fact that it's sigma 1,1. Right? To be non-sigma finite is to say that for every countable decomposition, for every purported countable decomposition, either it's not a cover or one of the pieces it does not have finite measure. And so it looks like there is a universal quantifier over reals there, right? Not sigma finite means there is no countable thing. So it's a surprising part to me, upon first inspection, was that it's sigma 1,1. That it's difficult, that sort of confirmed my experience. It was difficult to work with. I would have been astonished if it were an arithmetic property. But after the fact, after looking at it, the fact that it's sigma 1, 1 is not so surprising. Here's a good analogy to a much more familiar situation. So, and this is, once you think of doing the index calculation, this is a fairly obvious thing. If you look at, suppose you have look at the problem not of being not sigma finite, but of being not countable. Right? The set of indices for closed pi 0, 1 subsets of the Cantor set such that C is not countable, right, is sigma 1, 1 complete. Right? And being uncountable, a closed set is uncountable. You don't need that universal quantifier. Right? It is actually an existential property. A closed set is uncountable if and only if it has a perfect subset. Right? So that's Cantor's theorem. So I never thought of, until like this, I never thought of Cantor's theorem as improving the index set calculation, but it certainly does. Right? So you can tell whether a set is uncountable by asking whether it does it. I have a subtree of 2 to the less than omega. Is the set of paths through that tree uncountable? Well, yes, it is. If and only if it has a perfect subtree, which is a sigma 1, 1 property. Okay, so that way of understanding uncountability can be applied to understand non-sigma finiteness. But you have to go through it takes a little more, the technical work is a little more involved. But it shows up in the ingredients of the capacitability theorem. Right? Davy's proof about capacitability of non-sigma finiteness entailed developing the following. If you have a closed subset of a set that's closed with regard to linear measure, well, that closed set is non-sigma finite if and only if there's a perfect tree of closed sets such that each path through that tree corresponds to a closed subset of C. I should have said that each of these things, a closed set, which is a subset of C of positive linear measure. Okay, so it's like the Cantor theorem. A closed set is not countable if and only if it has a perfect subset. A closed set is not sigma finite if and only if it has a perfect tree, and these each path corresponds to a closed set, and for different paths, the closed sets are disjoint. I'm so used to thinking about perfect sets that I'm not saying everything that should be said. And 2 paths. Two distinct paths correspond to disjoint. Okay, so you have a perfect tree of closed sets, and then it follows C can't be sigma finite if it has an uncountable collection of closed sets of positive measure.
Sorry, and is there conditions on C, or is C is closed?
We're still talking. We're in this case study. C is a pi 0.
C is pi 1. Okay.
Yeah.
Okay. Thank you.
But this applies. This analysis applies to. This was in Davy's theorem. So actually, this works all the way up to analytic sets.
Okay.
Okay. So it follows that this not sigma finite is a sigma 1, 1 set. Right? You just have to put together. The set is not sigma finite if and only if there exists this way to put together a collection of this tree of closed sets, and to tell whether a path is positive measure we set as arithmetic. Okay. All right. So now the other part of the implication, of this proving that not sigma finite is sigma 1 complete is showing that it's complete, and there this ability to put together to take a set and decompose it into uncountably many for non-sigma finiteness, decompose it into uncountably many sets of positive measure. You do something along the lines again of taking unions of line segments. So you can work with the sets that are going to be a finite positive measure or line segments, and then you do the following. You reduce the problem for this. We need a sigma 1 complete property, a subset of, you take a infinite branching tree, and to say whether it has an infinite path is a sigma 1 complete condition. So we're going to reduce that to not sigma finite, and we do it in the following way. Given the tree T, we build a closed subset of the Cantor square, so that if the tree has an infinite path, then this closed subset is a union of uncountably many disjoint line segments. And it looks a lot like that little sketch I made for Besikovich's example. And if it doesn't have an infinite path, then C is a union of countably many line segments. And you have to follow all the possible paths in the tree. If sigma 1 is true, then one of those paths gives you the first option. If pi 1 is true, then every attempt to try to build in this uncountable collection of line segments terminates at some finite point. And at that termination point, what you've committed yourself to is only finitely many line segments. And then you get that the terminal nodes in the tree are a countable set, and that gives you the sigma cover. So it's you would think that I think this is about as far as we've gotten. So you'd think that this way of thinking about the notion of non-sigma finite as a kind of perfect set property, right? That's the way to get at the notion, because we do have an equivalence, at least for the types of sets that we have been looking at. But the problem about the Borel conjecture remains open, and I'd be happy to hear anybody's thoughts about it. And that is the end of the comments that I've prepared. So I'm happy to answer questions.
Thank you. So yes, questions. Peter.
So Ted, it seems like when you project these sets in one dimension, they have positive measure. Can you do that in such a way that they, in both dimensions, they look special? Or they're just a line segment in one dimension?
Let's see. So there are some theorems about this, about if you have a set of, I don't think that you can, no, I think the answer there is probably no, but I mean, the problems of projecting sets of positive dimension to lines, and sets in the plane to positive dimension in the lines, I think that, so I'm not an expert on this sort of thing, but I think the answer there is no. There's some theorems of Marstrand, I think, that are relevant.
So if I'm hearing you right, everything kind of looks like a union of lines, disjoint lines that have.
In the examples that we gave, yes. I mean, but of course, in general, that's not true.
Do you have a general example that's approachable?
A general example of what?
Where it's not the disjoint union of lines.
But of what theorem? I mean,
or just a set of strong positive measure zero.
Well, so the question so that for strong measure zero, the kinds of sets that people build are sets that are concentrated, it's like I said, there are the sets that are concentrated on the rationals. And most of these sets, look, you're not going to get you're not going to get any examples that are pathological within the realm of analytic sets, of sigma 1 sets. So almost all of these examples are axiom of choice examples, right? So that for strong measure zero or strong dimension zero, the examples that you take are like I said, an example so that it's uncountable, but every open cover of the rationals is an open cover of the uncountable set. So the set, sort of using the axiom of choice, you can cluster the points around the rationals. I know I said there's a lot of, but visual examples, I think there aren't any due to these classical theorems.
I would think anything that's visual would be arithmetic in some sense.
Well, at least within analytic, yeah.
There are other questions.
So, Ted, does non-sigma finiteness implies a perfect set property?
The non-CS for analytic sets, that's correct.
I mean, the reverse, does non-sigma finiteness imply perfect set property?
Yeah, so right, so let me go back to this, right? So if this set,
right.
Set is analytic, and non-sigma finite, then there is a perfect set. Property. So that's Davies' theorem.
Okay.
That's how Davies worked out the capacitability theorem.
But this is for closed set, right?
Analytic.
About for arbitrary set.
Arbitrary set? I don't know. I mean, the perfect set property is in the set, perfect set in the sense of this notion.
Yeah, I mean, for arbitrary set, if it's non-sigma finite, then it must have a perfect subset.
Well, it depends on. Do you mean just a perfect subset in the usual sense, or do you mean a perfect subset of closed sets?
For union, I guess. Oh.
So I mean, so if you're asking about just a perfect set, well, then there are. I haven't thought about that particular question, so I can't answer that question offhand. For an arbitrary, whether you can have a set that has non-sigma finite measure but has no perfect subset, I'd have to go back and look at the non-capacitability theorem and see whether that set has non-sigma finite measure.
Okay, thanks.
Okay, we have one more question.
Pardon me if you covered it already. So you're focusing a lot on the linear dimension. If these questions are answered for linear dimension, will that automatically flow to sort of knowing what's going on for all the different gauge functions with respect to the sigma finiteness question? Or are those also totally separate?
I don't see why it would. Yeah, it's the linear case is very tangible, right? So it's that's why I chose it. But no, it's unclear to me. I mean, we can give examples. These things are not these examples are not tied to linear. I mean, you can the kinds of instead of taking lines, it's very visually appealing to take these line segments. Where are we now? Back here someplace, I think, or maybe, well, maybe, oh, you know what, maybe it got erased. Okay, I can't find it offhand. Those examples are very visual, but you don't have to use line segments. You could use Cantor sets and change the dimension. And so but I don't see why this one, I don't see why knowing this for linear would give you the proof for all. And I don't see where linear is special, so I would guess that if you could do it for linear, you could do it for all, but there's no theorem like that. And it's interesting that this fact.
Okay, yeah, sure.
And then I'll quit. This fact that strong dimension is zero is the same as strong measure zero is very particular to it does not generalize. Right, so it's a problem. There are some things conceptually that you have the definition, but you don't really have an have an in your hands understanding of it or ability to work with it. I think that's part of the problem is getting some technical hooks into things. My guess is linear is going to be the typical case, but it might not be.
Oh, one quick question. Hi, Ted. So if you drop the sigma, so like finiteness, I mean, the characterization of S sets, is this for some reason trivial? I mean, to get like some sort of algorithmic characterization of, generalized S sets. So
Yeah.
I mean, because that looks doable to me.
If you drop the sigma, so I think the sigma finiteness is the interesting feature here.
So, is it completely trivial then if you drop the sigma, or is this just less interesting?
No, you know what I would guess that it would be trivial for if the gauge functions. I mean, not trivial, but my guess is that it would be that the ideas would carry forward if the gauge functions are nicely behaved. I haven't thought about it.
Okay.
I don't know of an obstruction, but I can imagine that there could be issues if the gauge functions are really pathological.
Okay.
But possibly if the gauge functions are nicely behaved, if they're C infinity or something.
Yeah, but that's the thing. You mean like for any function, I mean, it's like, I mean, you base on the set and you find the right gauge function. It doesn't have to be like nice behaving. It just needs to exist some gauge function for which
correct, yeah.
You have finiteness. I mean, it's from the other side, so you don't choose the gauge function.
I can't really hear what you're saying.
Okay, I'm sorry. Yeah. No, I mean that I wasn't thinking about just taking a fixed gauge function, but more like finding the right gauge function for a certain set. I don't know if that makes any sense.
Well, that is an interesting problem. I mean, there are natural examples that come out of Brownian motions where the gauge function, finding the right gauge function was an interesting problem. So I think, there are gauge functions do show up and for some naturally occurring situations. And it could be interesting to see how the algorithmic information theory, what insight it gives in those examples.
Okay, I think there's no more questions. So
Okay, thanks.
Thank you again very much, Ted.
Oh, you're welcome. Thanks.
And for those who are here, I think it's time for a coffee break now.